In this talk, I'll be relating recent work in the area of local first software to much older work that I did many years ago that overlaps with it, and see if there's anything interesting to be learned from all this. So the old work I'm referring to is a talk I gave at the Dynamic Language Symposium back in 2005 under the title of Objects as Software Services. And variations of that talk were given later at Google and at Microsoft Research and other places. And that was a fairly far-ranging talk that was focused on issues of over-the-network software update and software maintenance, but had significant overlap with the idea of local first software as well. And that's what I want to focus on today and see if I can learn anything from the new stuff or vice versa. So the idea of local first software is basically that modern applications that talk to the cloud tend to have problems when they can't talk to the cloud, as exemplified by this screenshot here. You have Google Drive, you don't have access to, say, the network, and you can't get at all your files that are stored there. And Firefox has all this advice for you what you can do, but basically it amounts to check your network. If your network doesn't work, you're up the creek. So as I covered in my original talk way back in 2005, there are these issues with these web or cloud-facing apps, chief of which is offline use, but not only offline in the strict sense that you don't have a network, which could happen, but you might have a network and it might not be fast enough. You might have a network that's too costly for you to really use. You might have a network that can't get to where you need to be because the site that you're actually trying to reach is down for whatever reason, or the site might not grant you access because your identity was hacked, or who knows, all kinds of things could happen. There's also the issue that we're really wasting an enormous amount of computing power and with it energy because all these devices that are talking to the cloud in these scenarios are often not using their full capacity. They're doing relatively little work compared to what they can do, whereas all this work is being done in a cloud data center, and that's inherently expensive and wasteful. There are all sorts of issues of privacy and data ownership and control and app ownership and control and so forth. So basically, it looks like there's room for improvement with this model. So my proposal was to try and combine the advantages of web apps and traditional client applications, personal computing in its classical sense. And that could be broken into two sub-goals. The first is this idea of software being always available. And this is where the overlap with local first software comes in, because that's really what they're focusing on. So always available means, yes, I can always get at it because it's on my machine and I don't, even if the network isn't working properly or the cloud isn't working, whatever, I can still access it. But it also had the opposite meaning that for web apps, they have a notion of always available, which is no matter where you are, as long as you have an access to some machine that's on the network, you can get at the app and the data, even if you're far away from your personal device, whatever it is. So we really want always to cover both those scenarios so that you'll be able to access your app and run it and reach your data from anywhere on the network, but also if you have a machine that you control and have installed your stuff on, then you can access things without the network. Now the other item was the idea of being always up to date. Web applications have this nice property that they download the latest version every time. They're always giving you the latest software. There isn't a question of old versions. There isn't a question of how do you get updates, how do you correct for bugs or distribute corrections and fixes and so forth. And that's very attractive, and that's something that native apps lack, actually. And so we'd like both of these, and this is less of a focus here, but it's an important property that we want to preserve. So let's take these in order and go into a bit more detail. So Local's first software, here exemplified by the heading of the paper from 2019 from the Onward conference by Martin Kleppmann and his associates, really focuses on this idea of always available. And it goes through the same reasoning that only much more extensively and with new perspectives on it that I went to in 2005. It basically points out that, well, okay, if we want to do this, we're going to have copies of the data on multiple machines, and then we're going to have to synchronize them, because these copies, assuming that this data is mutable, these copies will be changed independently, and we're going to have to reconcile them somehow so that we get all the changes from the different machines. And then, of course, we have this interesting problem that they might conflict. And they, unlike me, had a really good answer for this, which is to use conflict-free replicated data types, which didn't exist back in 2005, but even when I found out about them, I didn't really fully see their potential. But with CRDTs, it turns out that if you're clever, you can really do much more than I thought. A lot of data structures can be implemented and represented this way. And they do away with the problem of merge conflicts by definition. That's why they're called conflict-free. And that's a very elegant thing, because the best solution to a problem is to create circumstances where it cannot even arise in the first place. So to the extent that you can solve your problem with a CRDT, this is wonderful, and it solves the merge problem, and that's a huge advantage. Now, just to illustrate CRDTs briefly, here's the simplest possible CRDT, a counter, and it has increment and decrement operations that add one or subtract one from the counter, and a value accessor that'll let you view the counter. And that is basically all there is to it. And it has the nice property that, because essentially addition commutes, that no matter which order different clients play with this counter, when you reconcile them, they'll all converge to the same result, the same value for the counter. So this app, however trivial it is, can be synced without ever having a conflict. And this is kind of nice, and real CRDTs can do this for much more elaborate data structures, and that's very impressive and useful for this sort of thing. Now, the nice thing is, since you don't have a conflict, when you sync, you just play back the changes from other sites. Essentially, the CRDT libraries work by implementing something that is a CRDT, that it inherently doesn't have a conflict. And then they add to that the idea of persisting this CRDT data in some form, and in particular of recording the changes, which are intentional changes. They are the operations that are at the conceptual level of the data type, like incrementing the counter or decrementing it, as opposed to lower level operations, which just tell you that a value was set or a variable was mutated. And as a result, basically, you concatenate the change sets and play them back, and that's your sync process. And this can never fail because there are no conflicts, and everyone's happy. Now, if we contrast this with the idea of orthogonal synchronization that I had proposed back in 2005, we'll see some interesting differences. First of all, to clarify, orthogonal synchronization is essentially evolution or improvement, or whatever you want to call it, of orthogonal persistence. Orthogonal persistence basically had this idea that all persistent data is going to be automatically persisted by the platform. And it's persistent if it's reachable from some set of persistent roots that's predefined, and it isn't marked transient, because in a program, lots of data is cached, computed temporarily, and isn't really the business object that you want to persist in your database. And so these languages, these designs always had this idea of marking certain fields transient, so they will be excluded from the persistence process. But it is orthogonal to the data type. These things were conceived in contrast to proposals for, say, libraries in C++, where you had a superclass that handled persistence, and if you subclassed it, it would know how to persist your data. And you could only use those types of data to automatically persist things. And the orthogonal persistence school said, no, any data should be persistible, and you shouldn't have to worry about deriving it from a specific type. So clearly this is very different from CRDTs, because CRDTs, again, you're using specific data types for your purpose. Orthogonal persistence, you might look like something like this. Basically, the only thing is you have to distinguish transient and persistent data, and you could do this, say, with metadata here, or you could do it with a keyword. And that was all you'd actually see in the language that was different. Now, orthogonal synchronization, as I say, built upon this notion and said, in addition to persisting the data, we'll sync it. And as I said, it's antithetical to CRDTs because we're saying any data, we're not thinking about what data type we have to use. We somehow have a solution to sync everything. And again, the transient data plays in here because you don't want to sync it, but when you sync, you have to continue the computation. And so there's this idea that it gets lazily recomputed on every sync. And you can make that happen by, say, having a notion of a lazy field that has an initializer, and the initializer is computed the first time you access the field. And otherwise the field is nil. And so then when you sync, you can nil out all the transient slots, and they will automatically recompute whenever someone needs them again afterwards. And they'll be recomputed based on the latest persistent data that you synced up, so you keep everything coherent. Now, then what do we do about merge conflicts? The obvious approach doesn't work very well, because the obvious approach is to identify fields that are now conflicting when you merge, and or the fields that have changed, and if they've changed on multiple parties, then there's a conflict, and it's an extensional change, and you don't really necessarily know what to do about it, because it's basically being done at too low a level. It's being done at the level of individual objects. And so you don't really know how to decide if a conflict is really a conflict, and if it is, what the answer is. Well, how should you resolve it? Now, what orthogonal sync does do well, assuming you do find a solution to this conflict problem, is that it also handles this problem of keeping the software always up to date, which is something that has been outside the scope of the local first proposals, who haven't really been bothered by this very well. But we want to solve that as well, because it is a nice property of web apps that we want in this converged world of both web and native apps. And so the idea of orthogonal sync is that programs are data, and we synchronize that data. So we have a representation of programs as, say, class objects or module objects and method objects and things like that, and we synchronize them. And when we do that, we're essentially updating the application code live without a restart, without a reboot. And this fits very well with data migration, because now we change the program, and we change the format of the data, and we sync all the data that we already had, and basically update the representation of it while we're at it. So this is all very nice, but obviously, as I said, this approach seems very different from CRDTs and not compatible with it. And certainly, on the other hand, programs are not CRDTs. They are anything but conflict-free when you treat them as data structures and have them evolve. And so there's a question of how do these things relate, and how do we square this circle? So what I'm thinking here is that it's important to realize that the real difference here was that the CRDTs used a notion of intentional change that they were capturing. Whereas for general purpose orthogonal synchronization, you naturally would think of an extensional representation, because that's what you have. But if you're prepared to say, annotate the operations that are actual intentional changes, that are semantic changes, then you can actually track this. So, for example, if we were to write this counter and mark increment and decrement with metadata, indicating that these happen to be the operations that are represent the intentional mutations to the CRDT data structure. That metadata identifies what is a change and identifies a strategy for dealing with it. In this case, we're telling it it's a CRDT, and so we know how to deal with changes to CRDTs. But the potential of this is that we could mark things with other strategies. So it's open-ended. We can deal with things that aren't necessarily CRDTs if we can come up with a reasonable synchronization strategy for them. So the basic idea is we do orthogonal persistence and we sync periodically. And at a minimum, we're exactly where the CRDT people are, because we can mark our libraries with these annotations, and they're CRDTs, and no conflict arises, and all is well. But we do have the option of having alternate strategies, and the default would be an extensional merge, like we first suggested for orthogonal sync, where we just look at the fields and merge them, and if they actually conflict, we signal an error. And that may not be so bad as it sounds, because signaling an error implies asking the user, and obviously we don't want to burden the user with too many of these decisions. But if we really have a conflict, then we do, right? Conflicts if we're doing programming, certainly programmers have to resolve it, but even if we're doing a text document and we're meddling with the same text, two collaborators are touching the same sentences, the odds that we'll get a grammatical sentence out of this are probably not very good, and some human has to look at it and decide. And for the people who are writing it, that is not too burdensome, and it's probably better than having the thing blindly, mash up paragraphs and leaving them that way without you having noticed. Again, we should provide good tools for resolving this, change lists with infinite undo that tell you who changed what and when, and let you manipulate these changes conveniently. And then if this actually happens, and not too frequently, then I think we actually have a workable solution. We can, of course, extend this with other strategies like last right wins or things like that, if they make sense. The problem with last right wins is very often it doesn't. It's easy to think of, but it very often means that some valuable work you did got stomped on. So that's the basic idea of this talk, is to extend to implement orthogonal synchronization, but to use metadata to annotate intentional changes and thereby incorporate in particular CRDTs into that framework. And there's no downside to it, I'd argue, because you're getting what you get from CRDTs, but you now don't have to actually put the code for the calling out to writing out the changes and persisting them and so forth in the CRDT library. It's enough that you annotate, and the system can use those annotations to call the relevant code and do the work without you actually having to change the code that you're actually running. So there's lots of related work. There's the original talks, as I mentioned. There was the Vanadium project at Google that tried to do sync across languages and at very high performance scales, and despite a great deal of clever people and resources being poured into that, it didn't really meet those goals, and it was open source to live outside of Google or die, as the case may be, and I think it pretty much died. Fuchsia Ledger was a less ambitious approach to have support for that in the Fuchsia operating system. I think they've abandoned that as well. There is the very alive and well work that I've mentioned on local first software, and they have, in addition to various papers, there's the auto-merge software that actually does that by implementing a very general purpose CRDT that basically lets you do a CRDT for JSON. Though I do think there's times when the fact that there's no conflict isn't good enough, because it gets resolved, but not necessarily in the way that you might expect. So there's still work to be done there. There's a bunch of other interesting work that various people have done. Obviously, this relates to widely used things like operational transforms as used in Google Docs and others. There's the croquet work, which is not really a local first or an offline software. It actually depends on being online, but gives you very nice and very easy real-time synchronizations. So it's related but different. There's endless work on CRDTs, obviously. And so that's pretty much it. I wanted to call out some people who had looked at this problem with me back in the day, and especially Owen Kashai and Sebastian Krinsky. And that was all I had in this particular talk. I hope you found it interesting and maybe gives you an idea for how to actually try and implement some of this stuff. Thank you.